Not an infinite. Anybody? Well, when it was a totally infinite line, it was what? I over 2 pi rho h phi, right? If I have half of that line, it goes to, and you could plug it in, it goes to simply I, right, over 4 pi rho a phi. We can plug it in and improve that if you want. But in 4-7, you can plug it in. The limits at the lower one goes from 0, the upper one to infinity, and you're going to get this. You get exactly half. Make sense to everybody? Now, the problem, let me refresh myself with this, because here he says, he says 2 semi-infinite filaments on the z-axis lie in the region from minus infinity z to a. Remember, these start at minus infinity, they go to a. So for this problem, I have to draw it up. For this problem, you've got this. It comes in from infinity and stops at a height a. Here's the z-axis. Then at minus a, goes to infinity again. You all see this? And you're right here at a distance rho away. There's no current here to here. This is an odd problem, I must say that. And I want to know what the H field is here. Now,
Professor.
Yeah.
The problem looks like it goes to minus a, or goes to a and then from a. It doesn't look like there's a gap in between.
It's supposed to go from a to infinity and from minus infinity to minus a. And this is supposed to be a gap area, right? Isn't that problem?
Is that what it says in the problem?
I'll take a look, but I think it does. We'll take a look together. When it looks here, it says 2 semi-infinite lie from minus infinity to a and from a to infinity. He meant to say this should be minus a. See right here? He's got plus a. Because if you look at this, if you go from minus infinity to a, and then from a to infinity, that's infinite. There's no gap. He meant to say a minus a there. Are you with me, guys? He just messed up. So how do you do that one? Well, I might as well just point to the book and show you. Here, you can take this as the integration, the results for the integration. I hope you can see this okay. Got me glare. The lower limit here, I'll start with the one that goes from a to infinity, would be a to infinity, right? Are you with me? That would be the upper portion from a to infinity. You would have this lower limit as a, the upper limit as infinity. In fact, let me use this cursor. Lower limit of a, upper limit infinity. Then you would have to add from minus infinity to minus a. Can you all follow me? How many see that right there? Tyler, this is a good problem. Glad you asked it. Are you with me? Now, here's what you're going to find out. The integral from a to infinity gives you the exact same value as the integral from minus infinity to minus a, and it should make sense to you. You all believe that? So you just take one of those integrations and you multiply by 2. And that's what I'm about to do right here. I'm going to say that this H field right here, from this section right here, the H field itself would be equal to I rho over 4 pi over 4 pi. And then I have, on the a phi direction, now I have z over rho squared times square root of z squared plus rho squared. And it's evaluated from a to infinity. And this is the value of z going from a to infinity. Now, if you have infinity here for z, I want you to look at this. When z goes to infinity, or is going to infinity, then the z squared dominates rho squared here, right? Right? And as z is going to infinity, this becomes simply z squared square root, or z. Z over z goes to 1, right? It goes to just 1. And I'm left with what? I'm left with this I rho over rho squared 4 pi. So I have h here equals, and I'll take the I, then it's going to be over 4 pi. There's a rho squared and a rho, you're left with simply rho here. That's at infinity. Then when z goes to a, it's going to be, I can take the 1 higher, and then it's going to be minus. And remember, this is the only thing I'm worried about evaluating. It's 1 when z goes to infinity. And then when, well, I should say, I take the rho squared out there, so I can cancel that and that, right? And just have a rho in there. When this z goes to infinity, z over z squared plus rho squared is 1. And when it goes to a, it's just a over the square root of a squared plus rho squared. Y'all agree with that, Tyler?
How did you take the rho squared out?
Well, there's a rho here and a rho squared here. Rho is a constant, right?
Mm-hmm.
There was a rho up top and a rho
Right.
squared downstairs, so that would leave a 1 over rho.
Okay.
Now that's for the top one from a to infinity. But since the bottom one from minus infinity to minus a will just double that, I'll multiply this by 2. And if I do that, it just becomes 2 pi, doesn't it? 2 pi rho. Everybody in class, you see that? And this would be the H field that would be at a distance rho. It would be at z equals 0 in the xy plane. Y'all follow me on this? Give me a show of hands if you do, so I can see who's there. Fowler, you do? Tyler? Okay. Now, they ask a question in the problem right here. They say, what value of A will cause the magnitude of the H field at rho equal 1, z equals 0 to be half the value obtained for an infinite filament? Well, for an infinite filament, what do you have? Now I'm going to go back here. If I have an infinite filament, I have H equals to I over 2 pi rho A phi, right? Oops, sorry, can't see that. If you have an infinite filament, you're going to have this, right? 2 pi rho, I mean I over 2 pi rho in the A phi direction. Do you agree with me, everyone? If they want half that value, then it would be H equals I over 4 pi rho, right? In the A phi direction. So what value of A makes this happen? Now, if you look at this, what do you need? I come up here and I say, well, in order for this to become that, this has to be exactly 1/2, doesn't it? So what do you know? The A over square root of A squared plus rho squared has to be 1/2. You want 1 minus 1/2, which renders 1/2, right? Follow me on this. I need to make this quantity equal to 1/2. Everybody okay with that? Right? Because I want this value, I over 4 pi. Well, I've got I over 2 pi, means I have to multiply it by 1/2. To make that 1/2, 1 minus something is 1/2 means that something is 1/2. So this term, A squared, or A, pardon me, A over the square root of A squared plus rho squared has to be 1/2. And did they ask you for the value of A? Is that it? Or rho?
A.
A, well, now you can do what? You can go ahead and multiply both sides by the square root of A squared plus rho squared, right? And then you square both sides, so I have A squared equals 1/4, right? And then it would be A squared plus 1/4 rho squared. Correct, everyone? Then the only thing I do is take this to this side and subtract it off, so I have 3/4, right? a squared is equal to 1/4 rho squared, and I get rid of the 4, and therefore, if I want a, I would say a is equal to simply rho over the square root of 3. Do you agree with me, class? Because you divide by 1/3, and that would be the magic number. And I don't know if that one has an answer or not. Well, I only had the answer for the first one, but that's going to be the answer. This is a book. It's Haith's Electromagnetics Text. It's the 6th edition, and I thought I had the solutions for this, but I don't. I don't have it. But some of you probably can get it. I don't know. I can probably request the solutions, but that's how you do that one. All the rest of them, is there any other problems here you want to do? Because these are good problems. They're better, they're more challenging than Dr. Wentworth's problems, in my opinion.
Do you think we could look over 8.4?
Yeah.
The first part was relatively easy, but the second part I wanted to make sure I did right.
I'll do it. Something I'll tell you that, and I think by now you all know this anyway, that the way you learn engineering principles or physics or mathematics is just do lots and lots of problems. That clears up any ambiguity. And solutions help, but it's better to try problems without solutions first, in my opinion. All right, so this is 8.4. And here it says the filament is formed into a circle A. Radius A, it has a current I. And I know that the H field on the Z-axis right here, in general, the H field would be equal to I over 2 rho squared plus A squared to the 3/2 power. And then it's going to be, it's in the A phi direction.
Professor?
Yeah. Oh,
Switching?
yeah. Yeah, got it. This is in your book on page 218 if you're looking for where I'm getting this. And then it's going to be, oops, sorry. This is Z squared. Let me redo this. H for this one would be equal to I A squared over 2, and then it would be A squared plus Z squared to the 3/2 power. And this is in the A phi, or I mean AZ direction, pardon me. That's the H field anywhere on the Z axis if the loop is of radius A and the current's circulating that way. Now they want to know at the origin, so H, when Z equals 0, if you take a look at this, this would just be I over 2A, AZ. Y'all agree with that? Then in the problem, he asks, if a filament is shaped into a square at Z equals 0, and the sides are parallel to the coordinate axes, and current I flows in the phi direction, again, find H at the origin. So this is one of these things where it's the same length. So first you have to say, when we have that the circular ring, let me get you back. When I have that loop up here, I know the total length L would be 2 pi A. You agree with that, everyone? That's just the perimeter of that loop, right? Now I'm going to take that and bend it into and turn it into a square. So each side of the square would be the length divided by 4. If I take 2 pi a divided by 4, I have pi over 2a. So each side of this rectangle is going to be pi over 2a. This is pi over 2a. You all agree with me? Now it has a current I circulating this way. Basically, we've taken that circular loop and created, just turned it into a rectangle is the only thing we did. We refashioned it. And we want to know the H field right at the center here. Now, follow me on this. If you just look at this side for a moment right here, the far right side, my right, you all see that basically we have a finite length straight wire that's going to have an H field. And if you use the right-hand rule, I don't think I brought this up last time, but if you take your right hand and you put your thumb in the direction of the current, then the fingers will wrap around the direction the H field will be on your right hand. If you take a look at this, what that means is the H field will just be circulating like this and will be coming out of the page there. You all see that? In other words, it's going to be perpendicular, like in the direction of a pen standing right there. Can you all see that? And from the top one, if you do the same thing, the H field will coming straight out. If you come here and do the same thing, the H field will be straight out. And here, the bottom one, the H will be straight out. So that's additive. Make sense to everybody? Now, the way you get this is calculate the value of the H field at this point from one of these straight pieces of wire, one edge, and multiply it by 4. Does that make sense to everybody? All right, so what would it be from one edge? Well, how far away are you? What would that distance be, first of all? This is dead center, right? So if the total width is pi over 2a, this would be pi over 4a, right? So it would be rho equals pi over 4a. You all agree with that, class? Now you can go and I'm looking. I'll just tell you what it amounts to. If you look at this formula right here, this is the integration of this, the differential, and this is for straight wire. Now you make the lower limit minus whatever that, here's what it would be. If we just focus on this length, and let me do one thing. I want to get a fresh piece of paper to show you this. If I just have a side like this, where I'm going to say this is minus L over 2, this is L over 2 in length, and I'm out a distance rho, and I want to get the H field here. Well, I know that's going to be equal to I over 4 pi rho, and this is, I'm just getting that equation, evaluating it. And then you would evaluate z over the square root of z squared plus rho squared right there between minus L over 2 and L over 2. And this would be the H field coming out of the paper. And I guess it would be A phi in this case, if this is the Z axis. Can you all see this right here, class? All right, now evaluate it. That means H here would be equal to I over 2 pi rho. Rho is held constant. And then the upper limit is L over 2. So you would have L over 2 square root of L over 2 squared plus rho squared, right? And then it's going to be minus a minus, or then it would be plus L over 2, same thing. So you just multiply this by 2. And it would be in the A phi direction. Does everybody see that, class?
I have
Now-
a question, Professor.
Go ahead.
I think that h is equal to I over 4 pi rho square, not rho. Why it's just a rho?
Well, remember in the book,
Function.
take,
Yeah.
take a look at this. You see how there's a row up top? Do you have your book with you?
Yeah.
Look at it on page 216. All right. When you look at this, or equation 4.7, all right, you see it's I row, and then there's a rho square down.
Oh, yeah. Oh,
So
it's I rho.
that's where you get the 1 over rho term.
Yeah, I get it.
Now that would be, now you can put it, this would be the H field from this line, right? Now you can substitute in the actual values. For the one we had, the length of each side, right, was pi over 2a, right? You all remember that? This is from the page before when we turned the circle into a square, right? How many got that? Just I want to make sure you understand, right? We know we want to be halfway from the edge. So from any of these edges, we'd have a distance rho. Just put that down there. Rho would be actually equal to pi over 4a. And the L would be pi over 2a. And therefore, L over 2 would be pi over 4 times a. Now, this is what it is from one side, right? From 4 sides, it would be 4 times that. Do you agree? Class? Right? This is just one side. We have 4 sides in that rectangle or in that square, so we multiply by 4. And what that does is gets rid of that and just puts a 4 here. That means the H field at the center, if I reshape that into a square, the H field would be equal to 4i, and then L over 2 is pi a over 4, right? And then it's divided by pi, divided by rho, and then it's going to be the square root of, and here I have pi a over 4 squared. And it's going to be plus rho squared.
Did you
Now,
skip it down?
yeah, I'm gonna. I didn't put in for rho, but I will next. You can see rho is pi a over 4, so the H field itself at the center would be 4i times pi a over 4 divided by pi, and rho is going to be pi a over 4, and then it's the square root of pi a over 4 squared plus, and rho itself would be pi a over 4, so it's pi a over 4 squared. And now, are you with me so far? I'm just plugging in the values caused by the geometry. What do you see happening just by casual inspection? There's a whole lot of what going on? Cancellation. Don't you see these two canceling completely? Right? What about in here? Can't we just take out the square root, take out pi a over 4 and then put a square root of 2 down there? So what are you left with? Now I have 4i, right? Pi, and then I have pi a over 4 here, right? And then I have square root of 2 here. And if you want to, you can take the 4 upstairs and you get 16i over the square root of 2 pi squared a. And that would be the H field at the center. If you refashion that circular loop into a square. Follow me? How many see this? You asked it, Tyler. Do you follow me? These are good problems, and this is the kind of problem. These are more difficult problems because they're more complex. There's more parts to them. It's not a simple equation. You have to think through it. And you have to be attentive. Everybody good with that one?
Can you go up a couple steps?
Yeah.
So you have the general case where the row is pointing, where it's like h equals I over 4 pi rho and all that.
Hold on. Are you talking this?
Yes.
Okay.
Can you explain how you go from that one more time to the next line?
All right. First, I have to define what L is, right? L over 2. Well, L is the length of one side. And if you go back, remember, the circle had a perimeter of 2 pi rho, or 2 pi a, right? So if I take that and divide it by 4, it would be pi over 2a would be the length of each side of a rectangle, right? Or a square, right? So it's pi over 2a. Now, since that's the total length, half that length would be pi over 4a, right? So I put pi over 4a here and minus pi over 4a there, and I evaluate this. And that's what I got here, right?
Okay, you just go from 4 pi rho, and then you have 2 pi rho, and you multiply it by 2 again. And I understand you multiply by 4 for the general case, but where you cross off those two 2's, I don't follow that part.
Well, what I did, if I forget that, this would be for one side if we didn't have that 4 there.
Right.
The 2 pi was downstairs, right? Then when we evaluated this at L over 2, right? Just right here. When you put z equals L over 2, you get L over 2 over L over 2 squared plus rho squared, right?
Mm-hmm.
Then minus a minus L over 2. Well, minus a minus L over 2 is plus L over 2, right? Divided by the same thing. So it's just twice the first term. You're adding the same thing.
But was it not 4 pi rho on the denominator?
You know, you're right about that. That was a 4 pi. I know what, hold on.
I didn't know if I missed a step where you...
Well, let me get those constants out of there and I'll make sure it's right. This should have been a 4 pi to be started, right? Then I know this is going to come in twice, so I can make that just 2 pi, right? I mean, I over 2 pi and just leave it like that. That would be for one side, right?
Right.
And then I'd multiply this whole thing by 4. So really, if I multiply the whole thing by 4, this is awful messy, the net constant in front of there would be 2 over pi. And this is awful messy.
You might have just written the 2 and canceled it and then left it in the bottom. Previously, I don't know. That makes sense. That makes sense there.
This is for one side, right?
That's for 4 sides now.
Yeah, I'm sorry. You're right. Then that should be a 2. I believe that would be right then. I can give you the exact answer to this afterwards, or we can work through it. You don't have to waste a lot of class time on it. But that's the essence of what it is taking a finite length line and knowing what the H field is for that, and then multiplying it by 4.
Yeah, that's good. I was just making sure I didn't miss anything.
No, you're on it. You're right. Okay. Other questions? Let me take a look at that homework again, because these are good problems. Like Haight's book, a lot of times if I'm making out a test, I'll look there to see what kind of stuff he has. He's got a lot of clever things in here. Actually, 8.1 through 8.4 is probably the best ones for this set. I'll talk about this problem later when we talk about forces. But do you have any other questions before I continue with the lecture? All right. Something I'm going to say, and this is a perfect time for me to say this, that when you have electrostatic behavior and magnetostatic behavior, there are parallels that you see. I showed you how the Biot-Savart law was very similar to Coulomb's law, where we just had a differential electric field or a differential H field. There's one thing you remember with electrostatics that we covered. It was that if we had problems with the higher degree of symmetry, we could use Gauss's law to get the D field, and from the D field get the E field. You remember that? Gauss's law allowed us to really exploit symmetry. The integral of D dot ds over a closed surface was the charge enclosed. And I'm going to write that down. This was Gauss's law, right? Gauss's law was this. The integral of D dot ds over closed surface was the charge enclosed, right? Well, there's a parallel to it. And this is called Ampere's law. Now, Ampere's law states the integral of H dot dl over a closed loop is equal to the I enclosed. And this one takes a little more time to get to. So I'll give you this. These laws, by the way, were experimentally determined. You got to remember that. All this stuff is based on experiments. And this is Ampere's law. And in your book, we'll talk more about the solenoid and stuff in a bit that he has there, and the surfaces. But I'd like to get right to Ampere's law here because it helps. And what happens is this. Here's what this really means. When we have, remember with Gauss's law, we used that when we had problems with a high degree of symmetry, right? Cylindrical symmetry primarily. High degree of symmetry, and you're going to exploit this law. The integral of H dot dl is equal to I enclosed, and this is on page 224. The first one that they really show you is they're going to do the standard infinite line that you already know what the H field is from. So they're going to have an infinite line of current. And you all agree that that's cylindrically symmetric, right? If you have an infinite line of current, it's cylindrically symmetric. So I know the H field will not be a function of Z, but it will be a function of radial distance rho. Now, the other thing you have to do with Ampere's law is you have to realize something, that the H field from any differential amount of current, the direction of the H field you can always get with the right-hand rule. If I come out any distance from that current element and, radially away, I know that IDL, or if I take my right hand and I take the index finger and point it in the direction of the current, that would be IDL. And if I take that and then cross it into, or take my finger and through the smallest angle, go into the radial vector that I'm associated with the point of observation, IDL crossed a rho, or in this case, rho, will allow my thumb to point in the direction of the H field. Now you can see that IDL crossed in a rho will give me an H field in the A phi direction. Can you all see that, class? Can you imagine it in your head? How many can? In class, it's easy for me to do this, but take your right hand, IDL crossed in a row, your thumb points in the phi direction. And if you just move around the wire, you see that A phi literally changes the direction, its actual direction, but it'll always be perpendicular to rho and to the z-axis. That's important. Now, to apply Ampere's law to this problem, I would say the integral of H dot dl around a closed loop equal to I enclosed. Follow me on this. Well, the integral of H dot dl boils down to this. It would be H, which would have only a phi component, a phi. And then they're going to say dl here. Here's where I'm going. I'm going around a loop. And it's hard for me to draw this exactly, but it's a loop of constant radial distance rho. This is going to be my length or my path. I'll tell you where this comes from in a second, but it's a little, mathematically, I'm not sure it would help this, what I'm trying to show you here. Now, dl, you remember what dl is? If you have an arc length, that would be what? Rho d phi, a phi. Remember that, the differential arc length on the outer part of a circle? So it's dotted into rho d phi, a phi, and phi goes from 0 to 2 pi. That's equal to the current that's penetrating that loop. So when you look at this, if you actually filled in this surface, made it a planar surface, all the current that's piercing that surface normally would be inside the radial distance rho. That's this I enclosed right here. In our case, it's just I. So you can see that this integration, when I have a phi dot a phi, it's 1. Rho is a constant, so I end up getting the perimeter, which is just 2 pi rho, times h phi is equal to I, and therefore h phi is equal to I over 2 pi rho a phi. That's what it is. Now, do you remember we came to that same conclusion when we did the integral of a differential, the differential H field from a differential amount of current, and we integrated it from plus to minus infinity, or minus to plus infinity. Y'all remember that? How many do? We just did it, right? We got the same answer, but this is easy to get using symmetry and Gauss's law. I mean, Ampere's law. And you remember with Gauss's law, we got the same, we got the integral of d dot ds was the charge enclosed. We got the d field from an infinite line of charge exploiting symmetry, and it was equal to simply rho L over 2 pi rho. And then to get the E field, you divide by epsilon. Y'all remember that? But this is using, it's applying Ampere's law. Let me show you where this really comes from. It might give you a little better perspective on why we're doing it. I'm not certain, but I hope it does. What really goes on is this. There's a fundamental law. This is called the differential formula, and it's the curl of H for electrostatics is just equal to J, and J is the current density. This is a differential form of a law. Now, the curl operator isn't something you're very familiar with, but you will become very familiar with it. Well, if I integrate J over a surface, say you got a current J here, and you wanted to find the H field, but there was some degree of symmetry, the H field around any kind of a loop. Well, there would be a surface here that the current would be piercing. So if I integrate curl of H dotted with ds over this surface associated with this interior to that circle, that would be equal to the integral of j dot ds. Well, the integral of j dot ds over that surface is the amount of current that's inside that loop, that's piercing it. This Stokes' theorem says the integral of curl of h dot ds really is the same thing as the integral of h dot dl around a closed loop. And then the integration has to be in the counterclockwise direction. So if you're looking at the loop from your aspect angle, you're always integrating h dot dl in a counterclockwise direction. And that would be the integral of j dot ds. Well, that is actually the I enclosed, or the I penetrating that loop. Y'all follow me, class? Now, it's best to show this off with problems, because once you see how it's applied to different problems, you get an appreciation for Ampere's law. Are you ready? So now, He shows the problem I just did. To basically find the H field at a given distance rho from an infinite line of current right here. And then next, he's going to do this. Now, this is a little wacky, but I'm going to try to explain this using his pictures. Suppose I have a sheet of current. Now, hear me. I'm going to draw this, but I want you to see it in his book. He says if we just have the XY plane, in the direction of that arrow, we have current. But the current isn't going to be in amps, just amps. It's amps per meter. So as I go in the Y direction, I'm going to have so many amps per meter flowing in the X direction. You follow me? As I open that wider and wider, all the currents flowing in that direction, K are on the X axis. Can you all see this? And the symbol K is used to indicate surface current density. It's a vector. It has a magnitude and a direction. It could be like 10 amps per meter. So if I go over a 1 meter section of this, 10 amps would be flowing between here and here. Go over 2 meters, 20 amps, and so forth. With me on that? Okay. Now, if you do the surface problem, and I'm going to try to draw this now. If I have a surface of current, and I'm going to go right at the edge of it. Suppose I have current coming out of the paper like this, and it's constant, right? Call it K. K, and this would be amps per meter. And call this the X direction, call this the Y direction, and call this the Z direction. I hope you can appreciate, this is a rough sketch, but I'm trying to replicate that figure on page 226, if you got your book, figure 416. Now, I'm going to use the same thing as before. The integral of H dot dl over closed loop is the I enclosed. And here's what I'm going to do. Make a little rectangular box, symmetric with this axis, or symmetric with the XY plane, and call the height H, and call the length here, call this W. Now, here's something you need to do as a class. We all need to take a look at this. If you want to know the direction of the H field, first, if it's an infinite, think back to when we had an infinite plane of charge. What was the one feature of the D field from an infinite plane of charge that's unique to just the infinite plane of charge? No other geometry has this. What's the D field above an infinite plane of charge? An infinite plane, class? You remember? It's just rho s divided by 2. And the E field is actually rho s divided by 2 epsilon naught. How many remember that? All right, the D field itself is just rho s over 2, and the E field is rho s over 2 epsilon naught. It doesn't matter how far away from the plane you get, the E field or D field are always the same. You with me? It's because the charge it's got an infinite extent to it. Now, same thing happens when we have an infinite surface, an infinite amount of current on the surface, or basically a surface that's got a current that exists from plus and minus infinity for both X and Y axes. All right, this is just an infinite source of current that's flowing this way. What happens is you're going to find the H field will only be in one direction. And if you're above the plane, you can use your right hand, put your thumb in the direction of the current, and your fingers will curl around the direction of the H field. So up here, the current's coming out like that. The H field will be this way. And if you're below it, the H field will be in the other direction. Are you with me? Just try to appreciate this. And I know a lot of this, no matter how many words you use to describe it, it doesn't make perfect sense until you see these laws, you see Ampere's laws apply to specific problems. Now, what that means is this. If we take a look at this particular loop I've drawn here, and we take the integral of h dot dl around that loop and say it's equal to the I enclosed. Well, right here, I'm going to do one thing. I'm going to take the limit as h goes to 0. Now, what that does is shrinks this down so that the lengths on the vertical axis right here are 0, basically. All right, I get rid of that. Still has to be true. And now when I go around this loop and integrate it, you'll notice I've got the h field in this direction. My dl integration is counterclockwise. So h dot dl really here on this lower one would be just the h field, h phi times the width. So this would be h phi times the width. I go up this way, it's 0. And then I go this way, and it's again, same thing, plus h phi times w. Or really, I can make it 2w h phi is equal to I, the I enclosed. That's the I flowing in the surface from here to here. And since the surface current density is K, it's simply K times the width W. Y'all see what I'm trying to do here? You got me on that? If it looks a little funny, look on page 226 and you can read through that. But I'm essentially doing what he's doing, I guess, without breaking the integral up formally like he did. And the one thing that happens is the W cancels and you get H, and I called it in the phi direction, but it's really going to be in, it's either above it, it's going to be in this direction, below it, it's in this direction. So above it, technically it's in the minus Y direction, and below it, it's in the plus Y direction, but I'm calling it A phi. So my H phi would be simply K over 2, and I can put A phi direction, just make this a bold vector. You all follow me on that? So that's how you get the H field from an infinite plane of current. And it's very similar in nature to solving for the D field from an infinite plane of charge. Now, the next thing is this. And this is a Wentworth thing. He'll show you, well, what kind of problems can this actually be used for? Basically, it's cylindrically symmetric problems. That's mainly it. If you take a look at this, if you have like current flowing in a cylindrical system and you want the H field anywhere, you always have to find the total amount of current that's piercing that cylindrical surface, all right? You know, if you take H dot dl, the actual surface that would be a circle, it would be a basically a plate, right? You have to find the amount of current that pierces that plate and equate it to 2 pi h. I'm going to do one of these. A matter of fact, let's do example 4.7, where he gives you the current is J naught rho in the AZ direction. So I'll try to draw it up here. I want everybody to take a look at this. So J is equal to J naught rho in the AZ direction, amps per meter squared, and it exists from rho greater than 0, less than A, and then J is 0 for rho greater than A. I hope you can see this, come on. So I'm going to try to draw this here. Basically, you got a region like this. It's infinite, and you have this current density J, and it's true all the way out to A. And then from A, beyond A, for radial distance beyond there, the current density is 0. Now, Ampere's law says the integral of H dot dl closed is equal to the integral of J dot ds, or the I enclosed. That's Ampere's law. When you take a look at this one, this is just, it's the same kind of thing that happened when we had Gauss's law. Remember, if you were in cylindrical coordinates, and you took the integral of d dot ds on the outer cylindrical surface, that was always 2 pi rho times the height, right? Times ds. Remember that? And if it was spherical, it was 4 pi r squared times dr. Right? Those integrations never change. Well, this h dot dl will always end up being 2 pi rho. It would be the perimeter of a circle of radius rho, always. And then it's times h phi. And that's equal to j dot ds. Well, that's the amount of current that's flowing or penetrating that surface created by the circle of radius rho, so this surface. So I come over here and I say that j dot ds, watch this, that's really, the j is given up here, and this part of the problem will be for rho less than a, greater than 0. So j is j naught rho az. Now, do you remember the differential surface associated with this? Well, it would be d rho, right, for sure. You got d rho, right? And then we have rho d phi, right? Remember, the surface would have a d rho and a d phi component, but you have to weigh d phi by rho because it's the outer edge of that wiper arm. Do you all remember this, class? And this would be in the AZ direction. Now, rho goes from where to where? Anyone?
0 to rho.
Exactly, not a, because we're limited to be at rho less than or equal to a. So it goes from 0 to rho, and phi goes from 0 to 2 pi. Now, some of the stuff I've got going on here. I don't really need to spend this much time, but az dot az is 1, correct? And then when we go ahead and do the integration of rho, we got, now notice this, you got rho times rho, or rho squared d rho. I'll put this down here. I'll have h phi is equal to, I'll take this 1 over 2 pi right here. And then I'm going to put j naught out in front. Now, when I integrate rho squared d rho, I get rho cubed over 3. And when I evaluate from 0 to rho, I just get rho cubed over 3, right? And then when I integrate d phi, I get phi from 0 to 2 pi is just 2 pi. Y'all agree with me? Guys? Okay. Now, you see the 2 pi cancels, right? And you can see one of these rows cancel. So I can say my h phi is equal to j naught rho over 3 for rho greater than 0, less than a. Now,
It's rho
It's
squared.
rho square.
I'm sorry, rho squared. You're right. Thank you. Rho squared. And I apologize. I'm time conscious right now, and I want to finish this one and mention one other thing. Are you with me on this one so far? So this would be rho squared. Now, the next part is for rho greater than a. In here, the integral of h dot dl around the closed loop is equal to the integral of j dot ds, but the surface is going to be finite now. It's going to have a hard limit. This integral will still be 2 pi rho h phi. On this side, though, what you're going to see is happening is now, it's a double integral. We have j naught rho in the az direction, dot, and then it's d rho times rho d phi az. But here, thank you. But here on this side, this is, I'm applying the h dot dl is just 2 pi rho h phi here. And the j dot ds, well, j is j naught rho az, right? and dotted into, and this is the differential surface, d rho times rho d phi az. And the limit on d rho goes from, now it's limited to what? From 0 to a, right? Not rho. It only goes out to a because that's where the current exists. Doesn't exist. I mean, there's no added current if we go for radial distance rho greater than a. Agreed, everyone? And phi is still from 0 to 2 pi, correct? Now, you can see that what's going to happen is the az dot az is 1. I end up with j naught out in front. I get rho squared integrated as rho cubed over 3, and I evaluate it from 0 to a, or we get a cubed over 3, right? And then when I integrate d phi, I get phi from 0 to 2 pi is just 2 pi. And I divide this by 1 over 2 pi rho to get h3. One of the things you see happens is the 2 pi cancels. And I can say rho inside. And so I have j naught a cubed over 3 rho. And here h phi varies as 1 over rho. And it's the same variation would be for an infinite line of current. And that's the same thing Dr. Wentworth has in his book. Are you with me on this? Now, I'm going to give you some homework problems on this. I'm going to also ask you to look at, in the book, I didn't do this, but I think you can follow through. Back here, I didn't go through the solenoid in the book on page 221. I don't know why this autofocus is not working very well right now. But it's on page 221. Come on. So this is the solenoid problem on page 221 that I didn't have time to get at. And the other problem was the infinite surface, but we don't need to do this part because we just used Ampere's law to calculate what the H field would be from a sheet of current. Do y'all remember that? We just did it, right? So we don't need to do that one. The solenoid we'll talk about, but it's just, you know the actual differential H or the H field from a loop of current, right? We'll now use that as the differential H field from a differentially thick loop and do an integration. We'll set that one up next time, but it's the building block approach. Find the differential H field from a differential chunk of current associated with your geometry and then integrate over the entire geometry to get the total H field. We'll do that, and I'll give you some problems. Now, does anybody have any questions? I'm sorry I started a little late, but I had some problems with the coffee. Anything, guys? Nothing? I mean, I'm going to give you some more problems. I'll try to make sure I put the solutions there for them. All right. I thought if you guys find a solutions manual for Haight 6th edition, let me know. I mean, I've got them in my office, but they're paper, they're not electronic, and I'd have to take pictures of it all to share with you. But I like to get you the solutions, or at least the answers to any kind of problems I give you. All right. Any questions at all?
Do we have a quiz on Wednesday?
I'll let you decide. How many? You're going to have to get a quiz either Wednesday or Friday. How many want it on Wednesday? How many want it on Friday? Friday has it. It's unanimous too. All right, Friday it is. It's fine with me. I haven't heard anything more about what's going on today about COVID or anything like that, but Auburn sent something out. I don't know if you guys received it. Let me find this thing. Did you guys get anything from the university today? Or not? A healthier Auburn University plan. Did you receive that? You got it today? It's about wearing masks and all this stuff. One other thing I got to tell you, in my other class, one of the students does have COVID-19. He's at home, sheltering at home. He got it at the beach, believe it or not. Probably at a restaurant. No, anybody here have COVID-19 or know anybody in your circles? Good. Hope it stays that way. Is anybody going to campus from this class? Okay, good. I'm glad to. What?
I've been a couple of times in the last few weeks.
For a class or for what reason?
Just to do homework or study.
All right.
So,
Well, the only thing I've done is fished at the Red Barn by that Ag Heritage Park, and I've gone to my office to get paper, and I may go up there today to get a few more books, but that's really all I mean, I'm not going to do any work up there that I can do at home. All right, well, if there are no other questions and stuff, then I'm going to get some homework out to you. And if you need to talk to me or see me, just let me know. I think you got my phone number, and you can email me however you feel comfortable. All right.